Hello and welcome to this lecture, which I like to call Fun with Matrices. It's basically a disjoint seeming set of facts about the kind of matrices that are important to us in quantum computing, which we're going to use to help us analyze quantum gates and how they can be combined into quantum algorithms. So let's begin with the hermitian conjugate. Here we have an example of a 2x2 matrix, an arbitrary 2x2 matrix. And on this, we are going to define the notion of a hermitian conjugate. Now, the hermitian conjugate is defined in terms of two other properties. One is the transpose. So the transpose of a matrix is where you basically flip the matrix along this axis. Everything below goes above, everything above goes below, and everything on the diagonal stays where it is. So those diagonal elements stay where they are, but in a 2x2 matrix, the off-diagonal elements get swapped. Also, we define the complex conjugate, which is simply the complex conjugate of all the elements. So all I have to do is rewrite out the matrix. I have copied the wrong matrix. So this should actually have B here, as in the original matrix, because all we're doing is the complex conjugate, and this should have C there. So that is the complex conjugate. Now if we do both of these things, if we take the complex conjugate and then of that we take the transpose, or equivalently, we take the transpose and then the complex conjugate, then we get the hermitian conjugate. So this, for a 2x2 matrix, is exactly what I was erroneously writing down before. So we have the elements in the same place as they should be for the transpose, and then we take the complex conjugates of them. So that's the hermitian conjugate. You'll be hearing more about that. Now let's move on to introduce the Paulis. The Paulis are the simplest but also the most important, arguably, gates. They're ones that come up all of the time. That is not a very good X, or S even. I can't write it, I can't say it. That's a much better S. Okay, so the Paulis are X, they are Y, and they are Z. And also, I'll draw it a bit further away, in some contexts, an honorary Pauli is the identity. So each of them has the property that if you square it, you get the identity. And this even holds for the honorary Pauli, the identity. And also we find that for any pair of them we have anti-commutation. So x times y is equal to minus y times x. And x times z is equal to minus z times x. And, there's another one, we might as well write it down. Z times y is equal to minus y times z. Also, if you multiply two of them together, you get the third one. So, consulting notes to make sure I get this right. I don't like y's, you see. I think I've already shown my bias against y's before. But there's no way of writing this relation down without having a y in there. So what we find is that z times x is equal to I times y. Or we could also have that x times z is equal to minus I y. And I leave it as an exercise to the viewer to work out all of the rest of them. But up to a global phase, multiply two of them together and you get the third one. So these are the Paulis. Okay, now let's return to our general single qubit matrix, although the properties we are going to look at also hold for any arbitrary matrix. But That's even more writing stuff out. So ABCD. Now this can be written as A times the matrix which has only a single element of 1 and the rest of them are 0, and the 1 is exactly where we want this A in our matrix, and B times the matrix which has a 1 only where we want a B, and I'm sure you can work out what the other two terms are, so let's skip past them. But the interesting thing is that all of these can be written out as outer products, and they can also be written in terms of Pauli's. So let's look at this 1, 0, 0, 0. This can be written as the outer product of this column vector and this row vector, which is the outer product of 0 with itself. And the next one, the one for B, 0, 1, 0, 0, can be written as the outer product with 0 with 1, and so on. So this just proves something that we've already really been using, which is that you can always write a matrix out in terms of outer products. Before, we've been using properties of the matrices we've been looking at to know how to write down those outer products, but this is a way of doing it which holds in all times and in all places and for any matrix, regardless of what its properties are, because we're just singling out each of the elements and writing down an outer product which corresponds to that particular element. And this is something that holds also for multi-qubit matrices as well, because you can write down the outer product of 0, 0 with itself, for example, which is the matrix which is a 4x4 matrix with a 0 up in the top, and a 1 up in the top, and zeros everywhere else. That's a lot of zeros to write out, and the subtitles will of course be on top of it. But there you go. Okay, so we can write them in terms of outer products, and these are the outer products that we have, at least for a single qubit matrix. We can also write down those exact outer products in terms of Pauli's, which is going to show us that everything can be written in terms of Pauli's as well. So the outer product of 0 with itself is 1, 0, 0, 0, which can be written as 1, 1 plus 1 minus 1, just so that this element, which we don't want, cancels out with this element. And the first matrix in that term is the identity. And the second matrix is Z. So we have rewritten this term in terms of Pauli's. Similarly, we can write down the outer product of 1 with itself as identity minus Z. But then how about something like the outer product of 1 with 0? Well, this can be written as x times the outer product of 0 with 0, because of course that x times 0 gives us the 1 that we desire. And that means that it's x times identity plus z. And x times identity is just x, and x times z is, consult the notes, minus I, never can remember which way the sign goes, times y. So this gives us two more of these outer products that are written in terms of Pauli's, and now we've even got a special guest star from y, And the outer product of 1 with itself is also going to come out as x, but in this case plus y. And so using these relations, we can write any general matrix down as some alpha times the identity plus some beta times x plus some gamma times y plus some delta times z. And the reason I'm not using a, b, c, and d as before is that these aren't going to be the same numbers as the a, b, and c and d, because these aren't the matrices that single out single elements, but there is a relationship between those numbers. But I'll leave that for you to investigate yourself, but hopefully it should be clear now that we can also write down matrices as sums of Pauli matrices. And similarly, if you have a term like this outer product of 0, 0 with itself, this is the tensor product of the outer product of 0 with itself and the outer product of 0 with itself. And each of those can be written as identity plus z. So you expand this out, and what you find is that this can be written as identity tensor identity, which is the 2-qubit identity, plus identity tensor z plus z tensor identity plus z tensor z. And you can do this for all other possible 2-qubit outer products, but also multi-qubit outer products. So it's also true that multi-qubit matrices can be written as sums of Paulis, but their notion of a Pauli gets extended to include tensor products of Paulis such as these. And of course, as the honorary Pauli, we have the identity. Okay, so this is how we can write down matrices in terms of outer products, but also in terms of Paulis. Now, let's talk about two specific classes of matrix which are defined in relation to the hermitian conjugate. So there's one class of matrix, and I don't want the highlighter at the moment. One of these classes of matrices is the class for which multiplying the matrix by its hermitian conjugate gives us the identity. And it doesn't matter which way around you do it. If a matrix satisfies this property, we call it unitary. And so I'm going to actually replace these m's with u's, because we're not talking about general matrices, we are just talking specifically about this class of matrices, which are the unitaries. Okay, so unitaries. There's a few fun facts about unitaries. One is, suppose you've got a state psi, and you've gone to the effort to normalize psi. So you know that the inner product of psi with itself is 1. Now someone comes along and applies u to psi, giving you some weird new state, phi. Now, is phi still normalized? Well, the inner product of phi with itself is the inner product of, and we already noted before that the effect that u has on the ket form of a state, u dagger, has the same effect on the bra form. So this is the inner product of phi with itself, but because of this in here, we can use this relation, and putting an identity in the middle of that just means that we're going to come out as the inner product of psi with itself, which is 1. So if you apply a unitary to a normalized state, then you get a normalized state back. But actually the property is more general than this, and I think it deserves a new slide. If we have a couple of states, psi 0 and psi 1, and we know the inner product of those, and perhaps we depend upon the inner product taking some certain value for some certain reason, then if we were to act upon this with u, turning psi into phi naught, so psi naught into phi naught, psi 1 into phi 1, then the inner product of psi naught and psi 1 would be exactly the same as, so the inner product of phi naught and phi 1 would be exactly the same as that for psi naught and psi 1, with exactly the same proof as in the previous slide. So what this means is that if psi naught and psi 1 are, for example, orthogonal, if they represent a basis which we can use to describe our system, then the new states that we get out of these, the psi naught and the psi 1, will also represent a basis. So we can think of unitaries as being transformations between different orthogonal bases. Whatever basis we care about, we can apply the unitary to it, and we can find what basis the unitary turns that into. So let's look at a few examples of this. One is the x. Again, I've got the highlighter on when I shouldn't have. So the x, we can apply this to our favorite basis, which is the 0, 1 basis. And what we find is it turns 0 into 1 and 1 into 0. So we have started off with a basis, we have ended up with a basis. All it's actually done is just change the ordering of the states, but it's a valid effect. We could also try out x on another basis, so another set of orthogonal states which spans all possibilities, which is the x basis states, plus and minus. And we find that x turns plus into plus, and it gives minus a phase of minus. So, well, that's another valid basis. We could have chosen to multiply our minus state by -1, and it also gives us a valid basis. And so these basis states only differ by global phases, but it is still a valid effect. And of course, we've been using exactly these basis transformations as a way of writing down the effects of the x in previous lectures. We've turned this first term into, so we've been writing down x is equal to 0 outer producted with 1, because this outer product describes exactly this effect. And then we've been adding to that the 0 outer producted with 1 the other way around, because it describes exactly this effect. And similarly, we can write down x as plus outer producted with itself minus outer producted with itself. So with any unitary, if it is turning, and we'll just look at a 2-qubit example here, but it's generally applicable. if we turn some state psi0 and psi1, which form a basis, so they're orthogonal, into some states phi0 and phi1. Why do I always use phi and psi when their names are so similar? You would think I would use some very different sounding ones, but it's because that's what other people do, you know. It is the quantum academia version of peer pressure. Yeah, and then we have the psi ones as well. And this is a way of writing down this state u. So u is equal to that. Maybe I should put a box around it to make it all a bit more clear. When we have multi-qubit states, we just have more states in our basis, so this becomes bigger, but it's all equally valid. Now, one particular basis of interest for any unitary is the eigenbasis. And the eigenbasis is the basis for which the unitary has no effect but to give global phases. And unitaries always have an eigenbasis. So for any unitary u, we can find a set of states which I'm going to call hj. And the reason why I'm using h will become clear later. And these are such that u acting on these hj's gives us just a global phase. So we know it's got to come out as a normalized state. So it's very limited in what it can do in terms of eigenvalues. But it can multiply it by a global phase, just like x applied to a minus state gives it a phase of minus. And so we can generally create global phases. And global phases can always be written as e to the I times some real number. So this is our eigenvalue and it's parameterized by this real number. And yeah, we have an eigenbasis. So this also shows us how u dagger u comes out as identity, because for u dagger the effect is to give us the complex conjugate of the phase, and everything else is the same. It's the same eigenbasis, and it's the same hj. It's just we are putting a minus in there to take the complex conjugate. And we can also write this all in what we call spectral form. So when we're writing down these mappings of the original basis to the new basis, when we're using the eigenbasis, then it's all nice and diagonal because we've got the same state on both sides, differing only by the eigenvalue. And of course we have to sum that over all of our j's, which is all of our basis states. So for 1 qubit it will be over 2 states, for 2 qubits it will be 4, and so on. So yeah, there you go. The spectral form of a unitary. That's going to come in handy. Now let's move on to the other special kind of matrix, which is defined in relation to the hermitian conjugate. I don't know why old slides pop up like that. This program is a bit glitchy. And they are hermitian matrices. And hermitian matrices are defined as matrices which are equal to their own hermitian conjugate. Now, hermitian matrices can also be written in spectral form. They also have eigenstates, but in the case of hermitian matrices, applying a hermitian matrix to some state does not necessarily give us a valid state. So one example of a hermitian matrix is, well, the inner product of 0 of itself. This 1, 0, 0, 0. If you take the transpose of this, it's the same thing. If you take the complex conjugate of that, it's the same thing. So this is equal to its hermitian conjugate. This is a hermitian matrix. But if you apply this matrix to the 1 state, what we get is 0. Not the 0 state, but actual 0. The number 0. Or perhaps more accurately, the two-dimensional vector 0. So that's not a normalized state at all. So we don't necessarily get normalized states out of these. In fact, this means that for the eigenstates, so if we apply a hermitian matrix to one of its eigenstates, which I'm going to call Hj, which makes a lot more sense in this case because I'm using H for the hermitian matrix, then these come out as any number multiplied by the Hj. But when we write it in spectral form, then one thing we'll note is that these numbers do have to be real. And the reason why they have to be real, we can see just by taking the hermitian conjugate. So the hermitian conjugate is a basis-independent quantity. So the transpose, it depends what basis you perform the transpose in as to what matrix you get out. The complex conjugate is also basis dependent, but interestingly, the combination of these two things is not basis dependent. Doesn't matter which basis you write your matrix down in. When you do the hermitian conjugate, the thing you get out is exactly the same. So if we do the transpose in the eigenbasis, well, doing a transpose when we're thinking about these inner products just means swapping the two states in each of these, outer products, means just swapping the two states in these outer products. And if we do that when we're using the spectral form, they're the same. So the transpose has no effect. So then all that's left is to do the complex conjugate. And in the eigenbasis, that means that we take the complex conjugate of the elements, which are the eigenvalues. And in order for us to have that the hermitian matrix is equal to its own hermitian conjugate, it means that the complex conjugates of the eigenvalues have to be equal to their own complex conjugates, which means that these values have to be real. So we have got two kinds of matrices: unitary matrices, which in spectral form can be written as e to the I times some real number for each of their eigenstates, and the hermitian matrices, which can be written as some real number times their eigenstates. And this is why I've used Hj for the eigenstates of both, because we can see some correspondences between these two things. Both of them, these should be outer products. Both of them are written in terms of outer products of eigenstates. Okay, that's not all that exciting, but the point is that both are parameterized by a set of real numbers. In one case, they are used as the eigenvalues themselves for the hermitian matrices, and in the other case, they're used to define complex numbers of magnitude 1. But in both cases, they exist. So this means that for any unitary, we can define a corresponding hermitian, and for any hermitian, we can define a corresponding unitary. And in fact, the way we write this down is to say that we can get a unitary, which is e to the I times a hermitian, where here this exponential is defined in the way that we do the exponential of a matrix. You know how an exponential is defined in terms of its Taylor series. If you just plug in the matrix into the Taylor series. That gives you the exponential of a matrix. And what we find if we apply it to something in spectral form, as we have here, is that when we do all of the things like when we square some of these outer products, we get the original outer product back. And when we multiply them from one term with another, then because they're orthogonal, and we get a 0. And what it means is that, we just get the exponentials of the eigenvalues, which is exactly what we want here. So we take the complex exponential of this matrix, and we get the matrix which has exactly the same eigenstates, but whose eigenvalues are exponentials of the original eigenvalues. So these ones here. Okay, now let's talk about Cliffords. So there are different types of gate, different families of gates that are useful for different things in quantum computation. We have already talked about the Pauli's, X, Y, Z, and as an honorary Pauli, the identity. There I've used a different convention for writing the identity than before. Oh well. Now another set of gates are the unitaries, which map Pauli's to Pauli's. So this means that, by conjugation. So if we conjugate a Pauli by a Clifford, and conjugate means that on one side we apply the gate and the other side we apply the hermitian conjugate of that gate, then what we will get is a Pauli up to some phase. So we might get, for example, that was supposed to be a wavier line. So we might, for example, conjugate an X by some Clifford and get something that is minus Z or Z or IZ, something like that. And in fact, the unitary which does this, and it does it up to equality, is the Hadamard. And similarly, the Hadamard turns Z into X, and it turns Y into, well, what's left? Y, but in this case with a minus. Yeah, this is not the only example of a Clifford gate. So another example of a Clifford gate is S. So if we do S, X, S dagger, then unless I've got my conventions mixed up, we get Y. If we do S, Y, S dagger, we get minus X, I think. I'm never very good with where minuses are. But it's, the basic idea that S transforms X into Y and Y into X up to some phase, and it's important here. And S, Z, S dagger, because S and Z commute, actually turns out to be just plain old Z. So with Cliffords we can transform Pauli's into each other. Now, Pauli's are pretty boring and cheap, so you might wonder why we might want to do this, but we will see some good uses of this later. But I should note that the notion of Pauli's also exists for multi-qubit systems. So for example, we might say have a Pauli which is not just a single qubit Pauli but a tensor product of Pauli's. So here's a 2-qubit example. And we can have Clifford gates which do something fairly boring to that. So we can have the equivalent of what we saw in the last slide, which is where it just turns it into Z tensor identity. But we can have something more interesting, so this will be a different unitary here, which takes X tensor identity and turns it into X tensor X. And in fact, you already know the gate that does that as well. It is the controlled knot. So here we have a few different examples of Pauli's. In fact, most of the gates that we've looked at so far are Pauli's. Oh, sorry, are Cliffords. Here are a few different examples of Cliffords. Most of the gates we've looked at so far are Cliffords. The Toffoli isn't though. There's one that isn't. Okay, so that's Clifford gates. And another example of an important family of gates is the non-Clifford. Oh, I should note, first of all, that another example of a Clifford gate, or another set of examples of Clifford gates, are the Pauli's themselves. If you do X dagger around a Z, for example, then the fact that Pauli's are hermitian, and this is something you can verify, means that this is the same as X, Z, X. And if we commute the X through to Z, that gives us minus Z X squared, and X squares to identity, so that gives us minus Z. So they transform Pauli's to Pauli's, but they do it in a rather boring way of just giving phases due to the anti-commutation. Okay, so we have Pauli's, and then we have Cliffords, which include the Pauli's, but also include other gates. And then we have the next set of gates, which is non-Cliffords. So it's everything else. So an example of a non-Clifford gate is a rotation around the x-axis by some angle. If it's pi, then we get an x, which is a Clifford. If it's pi by 2, then we get something which is also a Clifford. But if we get also minus pi by 2 as a Clifford, everything else is non-Clifford. Yeah. And we can also think about this property that any unitary can be represented as the complex or the matrix exponential of a hermitian. So we can have a matrix exponential e to the I times some hermitian matrix. And what is the hermitian matrix which corresponds to rotation around the x-axis by some angle? Well, it's x times theta over 2. And similarly, our y is, our y with an angle of theta is e to the I y by theta over 2, and similarly for Rz. Now if we have a case where we can do one of these rotations but we want another of these rotations, and we also have the ability to do Clifford gates, then this is one place where Clifford gates can become useful. So for example, what if we want to do an Rz by some angle theta? Well, this is equal to e to the I z theta over 2, but we can also implement that with a Hadamard conjugating e to the I x by theta over 2. And the reason for this is because the only difference between this gate and this gate are the eigenstates. the eigenstates for the e to the I z theta over 2 are the eigenstates of z, because the unitary and the hermitian share an eigenbasis. The eigenbasis of z are the 0 and 1 states. And in the other case for the ETI x theta over 2, it's the eigenstates of x. So all we need to do is transform this state from having the eigenstates of x to the eigenstates of z, and that particular basis transformation is performed by the Hadamard. So that's how this works. So we can take the ability to do a rotation around the x-axis and the ability to do a Hadamard and turn that into the ability to do a rotation around the z-axis. And also there's the trick that we can basically bring these two things. I've left off the Hermitian conjugate just because the Hadamard is equal to its own Hermitian, but for clarity I should add it on. We can actually bring these up into the exponent, because basically all it's doing is changing this eigenbasis. And that's a trick that we'll be doing also later on. So bringing it up into the exponent is just because all it's doing is doing a basis transformation, changing the basis of the matrices, and we're using the fact that this unitary has the same eigenbasis as the Hermitian that we're describing it as a complex exponential of, and so we can equally apply it upon the Hermitian as we can apply it on the unitary. Okay, so there you have some fun with matrices, but the fun doesn't end here. Although I do have to remember where the fun does go. Okay, so with Clifford's we can turn a rotation around x or y or z for a single qubit into one of the other rotations, but by using multi-qubit Cliffords we can make this even more interesting. So for example, let's suppose we have an e to the I x theta over 2. Actually, we'll start writing this as e to the I theta over 2 times x. Now this is what it looks like when it's applied to a single qubit. If we want to apply it to many qubits, then the matrix for that is obtained using a tensor product. So we can do a tensor product and a tensor product and a tensor product, and we've got, well, here a 4-qubit state. But we can equally do the same trick of moving everything up into the exponent, because the unitary and the Hermitian have the same eigenbasis. So we can write this also as e to the I theta over 2 x tensor identity tensor identity tensor identity. So with that in mind, what happens if we were to conjugate this gate with a controlled knot? And here, if we denote these qubits as qubit 0, qubit 1, qubit 2, qubit 3, this is going to be the controlled knot, which is controlled on qubit 3 and targeted on qubit 2, and the same over here. And of course this should really be the Hermitian conjugate of that controlled knot, but controlled knots are equal to their own Hermitian conjugate, so I've left it out. So we can take this and we can write it out again, but this time moving the controlled knots up into the exponent. So we get e to the I theta over 2, and then the cx 3, 2, and then this x tensor I tensor I tensor I, And here I'm mixing conventions for identities on the same slide. But when you write them out small, it's nicer to use an I. And these controlled knots have the effect that we discussed earlier, which is that by conjugating x tensor I by controlled knots, you get x tensor x. So this gives us e to the I theta over 2 x tensor x tensor I tensor I. Now this is not the same as doing this rotation independently on both qubits, because in that case we would get lots of terms with lots of different things in. Instead, this is an entangling operation. This is an operation which entangles those first two qubits, or the qubits numbered 2 and 3. And we can similarly conjugate by even more controlled knots and get ourselves a rotation e to the I theta over 2 x tensor x tensor x tensor x, all by the magic of controlled knots. And then we could apply some other Clifford operations and use those by conjugation to turn. So let's, for example, do a Hadamard on qubit 2, either side of this operation. So actually I'll have them over here. So a Hadamard on qubit 2 before that and then after that. And it should be the hermitian conjugate, so let's just add that in, even though it's the same thing. Then that Hadamard conjugates this x, turning it into a z. So we have e to the I theta over 2 x tensor z tensor x tensor x. So by just using the humble rotation around the z-axis, the x-axis, combined with all of the Clifford gates, notably the controlled knot and the single qubit Cliffords, which can transform x into z, z into x, x into y, y into x, then we can write down any arbitrary unitary of the form e to the I theta over 2 times, what shall I call them, p n minus 1 tensor p n minus 2 tensor a whole bunch of stuff tensor p 1 tensor p0, where each of these pj are drawn from the set of Paulis, including the honorary Pauli, which is the identity. Any gate of this form, big multi-qubit messy gates, we can get from those gates that we started with. And this is a pretty powerful gate set. Usually we don't think about designing algorithms specifically in terms of gates of this form, but we can prove that using gates of this form we can do anything. So if we can do anything with gates of this form, and we can make gates of that form by combining simple single qubit non-Cliffords with Cliffords, then just these gates that we know so far, rotations around the x-axis, the Hadamard, the S, and the controlled knot, we can do quite a lot. But we will leave it till next week to use this to prove that we can do anything. So we'll define what the concept of a quantum computer doing anything that a quantum computer can do is, and that is the notion of universality. And we will show that using this gate set we can achieve universality. and then we will also link that to a specific application which shows that quantum computers can also do things that are intractable for classical computers. And once we have that, we can start looking at specific applications.